We're going to start our unit on hypothesis testing. And to begin looking at that, we need to talk about confidence intervals and think about, well, what does that even mean? So first of all, a parameter is the thing that we're talking about. It's the statistic that we're interested in. And usually for us, that's going to be the mean. We want to use, basically what we want to do is we want to use a sample and see if some statement about the population is supported or not supported by the sample. And generally, we're going to want to be talking about the mean for whatever the context is. So our samples are going to be used to represent the population. They're a subset of the population. And generally, the more samples or the larger the sample size, the better the information that we have. So we generally are going to want larger samples. But there's basically kind of this law of diminishing returns. You know, eventually, like the sample size starts having a lesser impact the larger and larger it gets. Of course, the larger it is, the better. And obviously, a sample of 300 is superior than a sample of 30, but then a sample of 600, the impact from 30 to 300 is much larger than the impact of 300 to 600. So, and we'll see that in one of our formulas here. So our confidence interval is how certain we are that a sample contains within its distribution the population's true value. So, but we can never know what that population value is for certain. We can't know that. We can't make true statements. We can't say with 100% certainty anything about the population from a sample is absolutely true. We can infer certain things, but we cannot say with 100% certainty. So that's what the confidence interval has to do with. So let's talk about a 95% confidence interval. So this is going to correspond to a z-value of between 1.96 and negative 0.96. And this confidence interval means that we believe the population statistic lies somewhere within it. So I'm going to switch my color here for a second. So here's a 95% confidence interval right here. So what we're saying is that somewhere in this area, we believe the actual population value is. Maybe it's right there. Maybe it's right here. Maybe our sample was really, really good and got really, really close to the population one. So this is our curve here, our normal distribution is representing our sample. Maybe our population is actually right here. Now, we don't know where it is. It actually might be over here. Maybe it's outside of our interval. I drew that backwards. Maybe it's outside of it. And that's what this interval's trying to tell us is like how big of a spread over here in our normal distribution do we think our population statistic is? So a 99% confidence interval, notice the difference here. So like here's negative 2 standard deviations, here's negative 2 standard deviations over here. So a 99 confidence interval extends this area on our curve even more and gives us a better chance. So yes, we do have a better chance to have the actual statistic, the actual parameter in the sample. But look at the area there. Like if our population mean is right here and our sample mean is right here, that's pretty far away. But still we got a better chance there with the 99% interval. So some typical intervals that we'll see are 99, and now this could be plus or minus, a 95%, again, plus or minus, and a 90%, again, plus or minus, but it could be any. So let's say, for example, that we wanted an 80% confidence interval. Well, then what does that ultimately mean? Or how can we actually get our z values if we wanted that? Now, we can do an inverse norm to get it. Now, notice none of these inverse norms that I put up here are actually 95 or 99 or something. So what has happened is we have our curve right here, and I'm going to use the 80 to represent it. Here's our mean, but this is our sample mean, okay? So here's our mean right here for our sample. And I want an 80% confidence interval. Now that's going to be smaller than our, the other ones on the other side. So this represents 80%. So the area under here is 0.8. But what's the area over here and what's the area over here? Now between them, I know that there's 100% area under this curve. And I have 80% confidence that the mean, the actual population mean, is somewhere in this area. So if I subtract that out, that means there's 20% area that I don't know about. So that means 10% right here, and that means 10% right here. So how am I going to get that interval? How can or that z-score? And I'm going to do my inverse norm, and I'm going to use not 80, but I'm going to use 0.1. Now that's going to give me the negative value, but I'm just interested basically in that absolute value. So if I go ahead and bring up my calculator, and I'll show you on this calculator, I'll get out of this. I'll show you two ways to get that. So the inverse norm on this calculator is, if we press option, it's over here on stat and distribution. We want inverse normal, so normal, inverse normal, and I'm going to put in 0.1 here. Now that will give me the negative z-score. So we got negative 1.281. So my z-score, negative 1.281, is a z-score that I would use for this, plus or minus. We would want both, but we're mainly interested in, again, just that number right there. So that's how you find it. Now there is another way to find it, and I'll go ahead and show you that other way. So you could, in your calculator, go over to statistics right here. And when we're doing any of this hypothesis testing stuff, we'll go over to distribution, and we will do normal, and we will do inverse normal. Same idea. We want our variable data. Now, our tail, we'll probably want to just select left, but it doesn't matter. We could select right. Our area, that's going to be that 0.1 that I put in before. And now we're used to, for our standard deviation and mean, and putting in whatever the data says. But in this case, we're going to want a standard deviation of 1, and we're going to want a mean of 0. We just want to set our mean to be 0 and our standard deviation to 1 to whenever we're doing this hypothesis testing. And that will give us our z-score, and it's the same thing as I did earlier. Okay, so let's go on then. Okay, why not do 100% confidence? Well, remember that this distribution goes on forever. So being 100% confident is going on forever. Well, of course, the population mean could be way over here, but that's nowhere near our sample mean. So that's not really useful. Saying that we are 100% confident when we take a look at our sample, saying that has no meaning whatsoever. So we want a good balance between having a meaningful confidence interval and actually, being able to say, hey, we think with some certainty, well, I want to be careful of that word, but, we're close to where the population actually is. So we could generally be happy with a 95% confidence interval. That's still pretty good. And it's not like way out there on our distribution. Okay, so maximum error is going to be very important to us. And what this tells us is the maximum difference between the population statistic and the sample statistic within, our confidence interval. So here's our formula. Z is that score that we just talked about, how we get it. S is our sample. This is our sample standard deviation, and n is our population size. Now notice it's in a square root, and that's telling us that really as n gets bigger, there's a diminishing return to how much better our sample actually is. Okay, to get our confidence interval, we're basically going to take our sample mean. So that's what that is. This is our sample mean. And we are going to take our error, our maximum error, and add and subtract it from it. And that will give us our interval. So here's an example problem. I might not do all of these, but let's go ahead and try it. So a poll of 218 members on MySpace showed that they spend an average of 14 minutes on the social site with a standard deviation of 3.1. We're going to find, let's start with the 90% confidence interval, and then we'll work our way over maybe to do all three. So the first thing I'm going to do is I'm going to find my maximum error. So that's my E, and that's going to be ZS over square root n. So my sample standard deviation is 3.1. My sample size is 218, so square root 218. Now I'm going to need to get my z-score. Now to get my z-score, I'm going to do that inverse norm. And since I want 90%, I'm thinking, 5% over here, 5% over here, and that leaves 90% in the middle right there. So I'm going to go ahead and do my inverse norm of 0.05, and when I do that, I get negative 1.644. I'm just going to use the positive, and I'll round it. And I'm going to go ahead and type that in. And after I'm done typing it in, I do get an error of 0.3454. Okay, so now to get my interval, I'm going to take my X bar, my sample, and add and subtract my error from it. And that's going to give me my confidence interval. And this is for the 90% confidence level. So I would take the 14, and I would first subtract the 0.3454, and then I would add the 0.3454. So I'll go ahead and do that. Now, on the plus side, that's going to be easy. So we have 14.3454. And I'll put a less than equal to. And I will now subtract it. And I get 13.656. And that is my 90% confidence interval. Okay, let's take a look then. I'm going to hopefully clear all that. And now let's do the 95% confidence interval. So first thing I'm going to do, I'm just going to go ahead and get the z-score. The z-score is going to be the inverse norm of, now let's think about this. If I have 95% in here, then what do I have out here? Well, 2.5 and 2.5 on each side. So I'm going to inverse norm 0.025. So I'll go ahead and do that. And I'm only interested in the digits. I'm not necessarily interested in the sign. So I got 1.96 basically. And you'll probably want to memorize these z-scores for these because these are the confidence intervals that we'll be most interested in anyway. So to get my error, I'm going to do ZS over root n. So we still have our 218, and our z-score is 1.96. and our standard deviation of 3.1. And we'll just type that all into our calculator, and that will give us our error. So I'll type that all in. And get 0.4115. So now, to get the confidence interval at 95% level, I'm going to do my sample mean plus and minus that error. So notice I'm writing, this is the population statistic. That's going to be less than 14.4115. And on the other end, I'm going to get 13.588. There we go. And 99%, I'm not going to do all of that one, but let's just kind of think through how it would start it. If I have 99% right here, that means between this side and this side, I actually have 1% that I could use. So that's actually a half of a percent, and a half of a percent is 0.5. So what would I put in my inverse norm? I would put in inverse norm 0.005, and that will give me the score that I'm looking for. Okay, a poll of 422 randomly selected high school students found that they brushed their teeth an average of 11.4 times each week with a standard deviation of 1.6. We're going to find the 95% confidence and 99% confidence intervals. So first thing, I'm going to get that Z statistic for 95%, that's 1.96. So to get my maximum error, I'm going to do Z 1.96 times my standard deviation 1.6, and I'm going to divide by the square root of 422. So I'm going to put that formula right up here. So that was ZS over root N gives us our maximum error. So I'm going to type that in real quick. And we don't expect there actually to be a lot of room for error, and there's not. It's 0.15 and some change, 3. So my confidence interval at 95% level is going to be, I'm going to take 11.4 and I'm going to add and subtract 0.153 from it. So on the larger end, I'm going to have 11.553, and on the shorter end of that, I'm going to have 11.247. So there's my 95% confidence interval. So that's how sure I am that the population statistic lies between these two numbers based upon the sample. And the error that I'm going to allow for, that's kind of like an arbitrary number that I'm just choosing to be confident about. So Z, for the 99% confidence interval, I'm going to go ahead and do that using my inverse norm. And I get a score of 2.576. So my error is going to be 2.576 times my standard deviation, and this is my sample standard deviation, divided by my sample size, the square root of it, and that will give us the statistic that we are looking for, our error. And our maximum error is about 0.2. So That's going to give us 11.2 and 11.6 for my 99% confidence interval. Okay, go ahead and try this one, finding the 90% and the 95% confidence intervals. So pause it, give it a try, and then I'll walk you through it here in a second. And I'm going to go ahead. So my z-score at 90%, I'm going to inverse norm the 0.05. And that gives me a z-score of 1.645. That'll be good enough, which means my error is going to be 1.645 times my standard deviation, 1.1, divided by the square root of 156. So my error, my maximum error, times 1.1 all over square root 156 gives me 0.145. So what is my confidence interval? Oh, it is going to be on the large end 4.645. And on the short end, I get 4.355. So that's my 90% confidence interval. So notice when we do the 95% confidence interval that it is going to be, the 95% confidence interval is going to be like a larger spread right here. So that's what I was saying about a diminishing return. The larger this confidence interval, that confidence level, well, you're spreading out your possibilities a little bit more. So Z is going to be 1.96 and E is going to be 1.96 times 1.1 and divide by the square root of 156. And when we do that, just give me a moment, I get a confidence interval or an error level of basically 0.173 rounded. So that means my interval is between 4.673 and 4.327. And there is my interval. Okay, that wraps this up.